Section 3, we're moving up to the 5 major network device types and how each one exposes itself to programmatic control. Then we go into VLANs and 802.1q trunking, which you need to understand before we can talk about VXLAN, the overlay technology that modern data center fabrics are built on. This section combines the device knowledge from CCNA with the data center overlay concepts that are unique to the automation exam. Let's run through the 5 device types that make up a typical enterprise or data center network, because your automation scripts are going to talk to all of them, and you need to understand what each one does before you can automate it intelligently. Understanding the device's role tells you what API or protocol it supports, what data you'll be reading or writing, and where to look when something breaks. The switch operates at layer 2, the data link layer. It builds a MAC address table, also called the Content Addressable Memory Table, or CAM table, by watching which source MAC addresses arrive on which ports. When a frame comes in, the switch looks up the destination MAC in its CAM table and forwards the frame only to the correct outgoing port. This is far more efficient than a hub, which broadcasts every frame to every port. Switches use VLANs to create separate broadcast domains on the same physical hardware, and they run spanning tree protocol, STP, to prevent loops and topologies where redundant paths exist between switches. Think of a switch as the postal sorting room. It reads the address label on each package and sends it to exactly the right delivery bin. The router operates at layer 3, the network layer. It maintains an IP routing table, a structured map of which network prefixes are reachable via which next hop interface or IP address, and it uses routing protocols like OSPF, BGP, or EIGRP to build and maintain that table. Dynamically, routers connect different IP subnets together and handle inter-VLAN routing when configured as a router on ASIC, or when integrated into a layer 3 switch. The firewall performs stateful packet inspection, meaning it doesn't just look at individual packets in isolation. It tracks the state of entire TCP connections and UDP flows and makes allow or deny decisions based on both the packet's header and the context of the connection it belongs to. Firewalls also handle access control lists, NAT and VPN termination. The Cisco Secure Firewall Management Center, FMC, exposes a REST API that lets you create, modify, and deploy firewall policy across a fleet of managed firewalls programmatically. That's a legitimate 200901 exam topic. The load balancer distributes incoming client requests across a pool of backend servers using algorithms like round robin, least connections, or weighted ratio, so no single server becomes a bottleneck. Critical for any microservices or container-based architecture where individual services might have dozens of instances running simultaneously. And the wireless controller, either Cisco Catalyst Center or Meraki, centralizes the configuration and radio frequency management of all your access points, allowing consistent SSID, security, and RF policies across the entire wireless infrastructure. Every one of these device types has moved toward REST APIs and structured data interfaces. The next slide maps out exactly what those look like. Now that we understand what each device does, let's map out exactly how you talk to each one programmatically. This is where the 200901 exam gets very specific, so pay close attention to the pairing of device type with interface type. Switches running Cisco IOS XE support, SSH for traditional CLI-based automation. Tools like NetMiko establish an SSH session on port 22, send CLI commands, and parse the text output. This is sometimes called screen scraping, and it works, but it's brittle because any change to the CLI output format breaks your parser. The better approach on iOS XE is NetCon, Network Configuration Protocol, over SSH on port 800, which delivers structured XML data modeled by Yang schemas instead of freeform text. In Ansible, the cisco.ios_config module in the cisco.ios collection handles iOS switch configuration and abstracts away the SSH connection management. Routers on iOS XE also support REST-CONF. That's a RESTful HTTP-based interface to the same YANG data models that netconf uses. But instead of an SSH tunnel, you make standard HTTP GET, patch, put, and delete calls to the device's HTTPS port for 143. REST-CONF is very developer-friendly because it works exactly like any other REST API. This is the convergence point where the networking world and the software development world truly meet. Firewalls are managed at scale through the FMC REST API. Rather than SSHing into each individual firewall chassis and manually editing ACL lines, you make REST calls to the Firewall Management Center, and it compiles the policy and pushes it to all managed devices simultaneously. That architectural shift from per-device CLI to centralized API management is exactly the NetDevOps model the industry is moving toward. Load balancers expose their virtual server configuration, server pool membership, and health check parameters through REST APIs, which makes them ideal targets for automated blue, green, and canary deployments. Wireless controllers give you two primary paths: Catalyst Center's Intent API, which abstracts multi-site wireless management into high-level intent calls, and the Meraki Dashboard API, which lets you configure individual access points, SSIDs, and RF policies via REST. Notice the consistent pattern across all 5 device types. Every one of them has moved or is moving toward REST APIs and structured data. That's the direction the entire industry is heading, and that's exactly what this course teaches you to take advantage of.